Now what's really and truly amazing for power series, any power series that we will be looking at, is that it's possible to find a number which we're going to call capital R, so that whenever the distance between the x value we plug in and the center of the series is less than this R value, then our series converges. So over here in terms of pictures, I've plotted here C, the center of our series, and whenever we are within R units in either direction of that center, our series is going to be convergent. Conversely, if I'm looking at the distance between the x value that I'm plugging in and the center of the series, and that distance is greater than R, then our series is going to diverge. And so we'll have this behavior, divergent series, for anything that is this far away from our center in either direction. And last but not least is the question of what happens when that distance is precisely equal to R. And that is going to be something that's a little more difficult to determine. It's not actually difficult to determine in practice, but we don't have uniform behavior the way that we have here. In other words, at these points that are precisely equal to C plus R and C minus R, we're going to have to do some real investigation to determine if we have convergence or divergence at these particular points. Truly, we could have both of them converging, both of them diverging, or one of them converging while the other one diverges, and vice versa. So we'll have more interesting behavior precisely at these endpoints. But within this interval, we will always have convergence, and outside of that interval, we will always have divergence. This value of R that does that for this particular power series will be called the radius of convergence of the power series. And because of the ambiguity at the endpoints, if we have a question that's asking us to find the interval of convergence of the power series, all they're asking for is for us to do that additional investigation at these 2 points to determine if I have convergence or divergence specifically at these points. Again, an example is really helpful. Let's keep going with the example that we have, and let's see our mechanism for determining this radius of convergence, which is to use the ratio test, as we've seen in previous videos. So let's follow through the steps of that ratio test. Our first step is to determine the absolute value of the n plus first term. So in order to do that, we take the formula for the addends in our power series, and everywhere we see an n, we plug in an n plus 1 inside of parentheses. So that was right here and right here. Notice that we're not plugging anything in for x, that just stays put. Now we have to deal with the absolute value signs here, and as we saw in our example, there definitely are values of x's that I could plug in that would make this quantity negative and produce some positive or negative behavior coming out of this term. The example we saw was when x was equal to 3/2. So the n plus 1 doesn't need an absolute value sign. We're only plugging in positive numbers for n, so I don't need absolute value signs there, but I do actually need absolute value signs around this quantity, the x minus 2 raised to the n plus first power. But there's a little bit of a rule on absolute value and exponentiation. If I were to first take the value of x minus 2 to the n plus first power, and then take the absolute value after that, I'll get the same result as if I would have just taken the absolute value of x minus 2 and raised that to the n plus first power. And that's what's drawing this equality from here to here. After having worked through that example, the second step is a little bit easier, where we just want to determine the absolute value of the a sub n's. In terms of what we write down here, we just write down our general nth term, and the argument we made about where the absolute values are required and where they're not is exactly the same at this step as it was in the previous step. So if we're looking at the absolute value of the nth term of our series, it will be n times the absolute value of x minus 2, all raised to the nth power there. Step 3 is to take these two quantities that we've just determined and divide them and simplify. So when we plug in our answers for step 1 and step 2 here, we get this equation right here. And in order to make some reductions, we're going to take that quantity x minus 2 raised to the n plus first power and break it up like so, with the nth power right here and one more copy of the absolute value of x minus 2 over here. That allows us to see more easily the repetition we have in the numerator and denominator so that we can cancel and get something a little bit simpler at this stage. Step 4 is now to determine the value we were previously calling rho for the ratio, which is the limit of the thing we simplified in the previous step. When I compute that limit here, plugging in my answer right here from step 3, before I compute that limit, I want to take any terms that are involved in this expression that do not involve an n, and I want to move them to the front of the limit so I don't get confused, particularly when I'm working with power series and I have multiple variables going on. I might get confused about what I'm taking the limit of. Since the x minus 2 doesn't involve the n, I want to move it to the front of my limit sign as though it's a constant. Once we've factored out this absolute value of x minus 2, our limit gets easier to think about once again, and either through a L'Hopital's rule or an end behavior model, we see that this limit has a value of 1, and so the rho from step 4 is the absolute value of x minus 2. Now, if you'll remember back to our ratio test examples, in our ratio test examples, we got a number here. With power series, we're typically getting a function of x, which should make sense to us. For most situations, the x value that we plug in is going to determine whether or not this converges. And so we're getting some sort of ratio that depends on the variable x that we plug into the power series. Here in our power series for step 5, we actually have a little bit of work to do. We're going to take the rho that we found from step 4. We're going to set that rho less than 1, and the values of x that satisfy this inequality are going to be the values of x for which our series converges. When we do that here, take our rho value and set it to be less than 1, that turns into the inequality the absolute value of x minus 2 is less than 1. We can remove those absolute value signs by sandwiching the interior, the x minus 2, between positive this value and negative this value. So we come up with this inequality, negative 1, less than x minus 2, less than 1. And adding 2 to all sides of this inequality gives us that we will for sure have a convergent power series when we plug in values for x that are between 1 and 3. Similarly, we're going to have a divergent power series if we plug in values for x that are less than 1 or greater than 3, because our ratio test is inconclusive when our rho is precisely equal to 1, when x is precisely equal to 1 and equal to 3. So we know that this series converges on this interval, diverges if the x values are strictly larger than 3 or less than 1, and we still don't quite know the behavior of this series when x is equal to 1 and when x is equal to 3. If all that we're interested in is the radius of convergence of this power series, we would take our center, which for this power series is 2. 2 falls precisely in the middle of this interval of 1 to 3, and the distance between 2 and either 3 or 1 is 1. So if all we needed to know for this question was the radius of convergence, we would compute that distance, which is a distance of 1, and we would say that our radius of convergence is 1. If, however, the question asks us to find the interval of convergence, we still need to figure out the precise behavior of this power series when x takes on those values of 1 and 3. So the step to figuring this out becomes, let's just plug in those endpoint values separately and use any sort of series test other than the ratio test on the resulting series to determine whether or not we have convergent or divergent series. For example, when x is equal to 1 and we plug in that value, we end up with the sum, as n goes from 1 to infinity, of -1 raised to the nth power multiplied by n. Using the alternating series test, if you'd like, this is an alternating series where the limit of the absolute value of these terms is not equal to 0. So this is a divergent series. Similarly, when we plug x is equal to 3 in our case, we end up getting n times the quantity 1 to the n. 1 to the n is just a 1 all the time, and so it's sort of silly to write. So we can just think of this as the series that adds 1 plus 2 plus 3 plus 4 plus 5 for forever. And that's very clearly a divergent series, as the limit of our addends is not equal to 0. So for this particular power series, we have divergent behavior at both of our endpoints, and our interval of convergence would be 1 less than x less than 3.